Section 1. The feeling that something is gone. There is a moment that almost everyone has experienced, and almost no one can fully explain. You are standing somewhere ordinary, a kitchen, a street corner, the window of a car moving through a city you used to know, and something small happens. A smell, maybe. The particular angle of afternoon light. A song that drifts out of a doorway. And for just a fraction of a second, something in your chest does something strange. Not pain, exactly. More like the sensation of reaching for something that should be there and finding only air. The past presses up against the present like a hand against glass, and you can see it clearly, and you cannot touch it, and then it is gone again. We call this nostalgia, or grief, or memory, depending on the circumstances. But underneath all of those human labels, there is a physics question, and it is one of the deepest questions that physics has ever tried to answer. Where did that moment go? Not emotionally, not poetically, literally, physically. The moment existed. The atoms were arranged in a particular way. Light was bouncing off surfaces at particular angles. Sound waves were propagating through air at particular frequencies. All of that was real. All of that was physical. And now it isn't happening anymore. But does that mean it is gone? This is where physics gets genuinely strange, and genuinely beautiful, and genuinely difficult. Because here is what most people do not know. The dominant view among physicists, not a fringe idea, not a minority position, but the mainstream view that falls most naturally out of our best and most tested theory of space and time, is that the past does not disappear. It does not cease to exist when it stops being present. It is still there. Every moment that has ever happened is, in a very precise and physical sense, as real as this moment right now. The year your grandmother was born is not gone. It is located somewhere. It is as physically present in the structure of the universe as the chair you are sitting in, and yet you cannot get there. You cannot go back. Not because the past is too far away, not because we lack the technology, but because of something fundamental in the architecture of reality itself, something woven into the deepest laws of how the universe is built. That is what this video is about. We are going to walk through the actual physics, not hand-waving, not metaphor dressed up as science. The real thing, explained slowly and carefully, so that by the end, you will understand something that very few people ever take the time to understand. Why the past being real and the past being unreachable are not contradictions. Why they are, in fact, the same fact viewed from two different angles. Let us start at the beginning. Not the beginning of the universe, the beginning of our understanding. Because for most of human history, the question of where the past goes was not even considered a physics question. It was a philosophy question, a theology question, a poetry question. Physics was for falling objects and planetary orbits. Time was just background. The stage on which physics happened, obvious, universal, the same for everyone, everywhere, always. And then one man working as a patent clerk in Bern, Switzerland, reviewing other people's inventions, decided to think about what it would actually mean to synchronize two clocks in two different cities. And everything we thought we knew about time turned out to be wrong. But before we get to Albert Einstein and his quiet revolution, let us sit with the question a little longer, because it deserves the time. Think about what you actually believe about the past right now, before physics has said anything. You probably believe something like this: the past happened, and now it is over. It existed, and now it does not. The present is real, the past is gone, the future has not arrived yet. Only this moment, only right now, has genuine physical reality. Everything else is either memory or anticipation, but not actual existence. This view even has a name in philosophy. It is called presentism, and it is, in many ways, the most intuitive possible picture of time. It matches how time feels. It matches how we talk about time. When we say something is, we mean it exists now. When we say something was, we mean it existed, but does not anymore. The grammar of almost every human language on Earth is built on this assumption. The problem is that physics, done carefully and rigorously, does not support it. Physics supports something that sounds much stranger, that the past and the future are just as real as the present. That now is not a special physical category. It is a perspective, a location. And just as you would not say that Paris ceases to exist when you are in Tokyo, the past does not cease to exist simply because you are located in the present. This idea called eternalism, or the block universe, is not a New Age concept. It is not a spiritual belief dressed in physics clothing. It is the most natural reading of the most tested physical theory in human history. And we are going to build up to it carefully, piece by piece, so that by the time we get there, you will feel not just that you have been told it is true, but that you understand why it has to be. One more thing before we move on, and this is important for the emotional register of everything that follows. There is a version of this topic that is presented as terrifying. The past is frozen. You are locked out. Time is a prison. You are a prisoner, moving in one direction toward death with no possibility of return. That is one way to frame it. It is not the framing we are going to use here, because honestly, it misses what is most interesting about the physics. The more you understand about what time actually is, what it is made of, how it behaves, why it flows the way it does, the stranger and more extraordinary, the ordinary experience of being alive, becomes. Every moment you have ever lived is, in a very real sense, permanent. Not in a sentimental way. Permanently, physically, really permanent. The universe does not delete its own history. And that, when you sit with it long enough, is not terrifying. It is one of the most quietly astonishing things that physics has ever discovered. Before we go further, wherever you are watching this right now, drop a comment. Tell us your location and the time there. It is a small thing, but given what we are about to talk about, how every moment in the universe occupies its own permanent place in the structure of space-time, there is something lovely about marking the specific moment you first heard this. Also, if you have not subscribed yet, now is a genuinely good moment. There is a lot more to come in this one, and you will not want to lose your place. Section 2. What Einstein broke, and what he replaced it with. To understand why physics says the past still exists, you have to understand what Einstein actually did. Not at the level of he was really smart and things got weird, but at the level of the actual conceptual move he made, because it is one of the cleanest and most beautiful pieces of reasoning in the history of science. The year is 1905. Einstein is 26 years old. He is working 6 days a week at the patent office, reviewing technical applications and spending whatever mental energy remains on a problem that has been nagging at physicists for decades. The problem goes like this. James Clerk Maxwell had written down, in the 1860s, a set of equations describing how electric and magnetic fields behave. These equations are extraordinarily successful. They predict the behavior of light, radio waves, every form of electromagnetic radiation. They are still in use today, but they contained a puzzle. Maxwell's equations predict that light travels at a specific speed, roughly 299,792 kilometers per second, but they do not say relative to what. In Newtonian physics, the physics everyone believed in 1905 velocities add up. If you are on a train moving at 50 kilometers per hour, and you throw a ball forward at 30 kilometers per hour relative to the train, the ball is moving at 80 kilometers per hour relative to the ground. Simple. Intuitive. Obvious. So, if light moves at 299,792 kilometers per second relative to something, and you are moving toward the light source, shouldn't you measure the light coming at you slightly faster? And if you are moving away, shouldn't you measure it slightly slower? Experiments said no. Light always came out the same speed, regardless of how the observer was moving. This was not a small discrepancy that could be explained by experimental error. It was a clean, reproducible, categorical result. The speed of light is constant for all observers. Most physicists in 1905 were trying to explain this result by postulating some medium, the luminiferous ether, through which light traveled, and through which the Earth happened to be moving in just the right way to make the measurements come out strange. The ether is how you save the intuitive picture of velocity addition. You just need to find the right background medium and the right correction factors. Einstein did something different. Einstein took the experimental results seriously as a fundamental fact rather than as a puzzle requiring a complicated explanation. He said, what if the speed of light really is constant for all observers? Not as an approximation, not as a coincidence, but as a deep law of nature. What would have to be true about space and time for that to be possible? He worked out the answer. And the answer was that space and time cannot be absolute and independent the way Newton assumed. They have to be flexible. They have to be relative. Specifically, if the speed of light is constant for all observers, then two observers moving at different velocities cannot agree on what is simultaneous. They cannot agree on which events happened at the same time. They will disagree, not because one of them made a measurement error, but because simultaneity is not a property of events themselves. It is a relationship between events and observers. This is the crucial move. This is the thing that changes everything. In Newton's picture, now is universal. When it is Tuesday afternoon on Earth, it is also Tuesday afternoon on Mars, on a spaceship halfway to Alpha Centauri, everywhere. The present moment is a single global fact. Time is a river that everyone is floating on together, at the same rate, in the same direction. Einstein showed that this picture is wrong. There is no universal now. Two observers moving relative to each other will disagree, systematically and measurably and correctly, about which events are simultaneous. And this is not a matter of communication delays or observation lag. It is a fundamental feature of how time works. Let us make this concrete with a thought experiment, because the abstract statement is easy to nod at and hard to actually absorb. Imagine a train car moving at, let us say, half the speed of light. In the exact middle of the train car, there is a light source. At the moment the light source flashes, the train is passing through a station, and there is an observer standing on the platform, watching. From the perspective of someone inside the train, the light flash travels equal distances to the front and back of the car and arrives at both ends simultaneously. There is no reason for it to arrive at one end before the other. The light source is in the middle, and the car is at rest relative to the passenger. From the perspective of the observer on the platform, however, the train is moving. The front of the car is running away from the light pulse. The back of the car is moving toward it. So the light reaches the back of the car first, and then a moment later reaches the front. Both observers are correct. There is no error, no illusion, no trick of perspective that can be dismissed. The passenger correctly observes the light reaching both ends simultaneously. The platform observer correctly observes the light reaching the back end first. These are two physically valid descriptions of the same events, and they disagree about whether those events were simultaneous. What this means, and Einstein worked this out completely, is that there is no absolute now. Different observers, in valid states of motion, will draw the line of the present moment in different places across the universe. What one observer calls the past might be what another observer calls the present or even the future for distant events. This is deeply, genuinely strange, but it gets stranger. Because if now is not a universal fact, if different observers can correctly disagree about what is happening at the same moment, then the present cannot be a special ontological category. It cannot be the case that now is the only thing that is real and everything else is gone or not yet arrived, because which now would that be? Whose now gets the privilege of being the real one? The answer physics gives is none of them, or equivalently, all of them. All moments are equally real. All events that have occurred or will occur exist with the same ontological status. They are all located in the structure of space-time. Some of them are in your past, some are in your future, some are elsewhere in a way that has no clear temporal relation to you at all, but none of them are more or less real than any other. This is the logical consequence of special relativity. It does not require a mysterious extra postulate. It falls out of the math directly. When physicists Hermann Minkowski worked out the geometry of Einstein's special relativity in 1907, he showed that the right way to think about the universe was as a four-dimensional structure, 3 dimensions of space plus 1 dimension of time that he called space-time. And in that 4-dimensional structure, every event has a location. Every event is a point in space-time. And points in space-time do not come and go, they simply are. Minkowski himself put it this way, in a lecture in 1908, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. That union is space-time, and in space-time, the past is not gone. It is simply there, located at certain coordinates, just as surely as a city on the other side of the planet is located at certain coordinates. You cannot visit it from where you are, but it has not ceased to exist. Now, there is an important thing to be careful about here, because this is the point where people sometimes feel cheated. Okay, you might say, but Minkowski's spacetime is just a mathematical model. It is a useful framework for calculation. It does not necessarily mean the past literally exists in some physical sense. This is a fair challenge, and the response is that physics does not work on this distinction very cleanly. When a mathematical model makes accurate predictions about every experiment ever performed, when it correctly describes phenomena that were unknown at the time the model was developed, when every attempt to falsify it has failed at some point, the model is what we mean by physical reality. General relativity. Einstein's extension of special relativity to include gravity has been tested to extraordinary precision. It correctly predicted the bending of light around the sun, the existence of gravitational waves detected directly in 2015, a century after the theory predicted them, the precise timing of GPS satellites, the behavior of black holes. To say that the space-time structure it describes is merely a mathematical convenience rather than actual reality is a philosophical position that is difficult to maintain in the face of that evidence. The block universe is not a metaphor. It is the most literal reading of the best physics we have. But we are getting ahead of ourselves. We have established why relativity suggests the past still exists. We have not yet talked about what the block universe actually means, what it looks like, what it implies, and why the fact that the past is real does not automatically mean you can visit it. Let us build that picture now. Section 3. The block universe, a cosmos that never erases. Close your eyes for a moment metaphorically, since you are watching this, and try to change the way you think about time. You are used to thinking of time as a flow, a river. The present moment is a boat, moving downstream from past to future, and the banks of the river are what you can see from the boat at any given moment. Behind you is what has already passed. Ahead is what has not yet arrived. Only where you are right now, only the present moment, is directly experienced. This is such a natural image that it feels less like an assumption and more like a simple description of reality. But it is an assumption, and physics does not support it. Now try a different image. Imagine a loaf of bread. The whole loaf, not just one slice. The loaf has length, width, and height. If you slice it, each slice is a cross-section of the loaf, a two-dimensional face of a three-dimensional object. No one slice is more real than any other. The middle slice does not become unreal when you eat the first slice. The last slice does not fail to exist, simply because you have not cut that far yet. The whole loaf exists simultaneously. All of it is real. All of it is there. And the fact that you are currently eating a particular slice does not grant that slice some metaphysical priority over the others. Now extend this image into 4 dimensions. The loaf is the universe. The length, width, and height are the 3 dimensions of space, and the 4th dimension, the one we usually think of as time, is just another dimension of the loaf. Each slice of the loaf, when you cut it perpendicular to the time dimension, is a 3-dimensional cross-section, the universe at a particular moment. The past is an earlier slice. The future is a later slice. And all of the slices exist with equal reality within the 4-dimensional block. This is the block universe. This is what physicists and philosophers mean when they talk about eternalism. And while the loaf of bread image is only an analogy, the actual geometry of spacetime is more complicated. As we will see, it captures the essential idea that all moments of time exist simultaneously, in the sense that all locations in a 3-dimensional object exist simultaneously. Now, the first and most natural objection: if all moments exist, why do I only experience this one? Why does it feel like time is flowing, like the present is special, like the past is genuinely gone and the future genuinely has not happened yet? This is a profound question, and we will return to it in depth later in this video. But let us gesture at the answer now. You experience only one moment because you are a physical system embedded in space-time, not an external observer of it. Your brain, your body, your entire capacity for experience exists at a particular location in 4-dimensional space-time. From inside the structure, you can only access information from your past light cone, that is, events that could have sent a light signal to your current location. You cannot access information from elsewhere in the block because your physical processes do not extend there. Think of it like this. A character in a novel exists on a specific page. They can only know and experience what has happened to them up to that page. They cannot read ahead. They cannot go back to page 3 and experience those events again. But the events on page 3 are still there. In the book, they have not ceased to exist simply because the story has moved on. You are embedded in the block universe the way a character is embedded in a novel. You are not watching it from outside. You are in it, at a specific location, with access only to what your location makes accessible to you. This analogy has limits. The physics is richer and stranger than a novel, but it captures something important. The felt experience of time flowing is not evidence that time actually flows in the way a river flows. It is evidence that you are a physical process that develops through time, and that development has the character of unidirectional progression. But unidirectional progression through a static structure is not the same as the structure itself changing. Let us go deeper, because the block universe raises questions that deserve careful answers. Question 1. Is this just philosophy? No. The block universe is not a philosophical interpretation layered on top of physics. It is, as mentioned in the previous section, the most natural reading of the mathematics of special and general relativity. When you write down the equations of general relativity, what you are writing down is a description of a four-dimensional space-time manifold, a geometric object in which all events, past, present, and future, are simply points. The equations do not have a present moment as a special element. They describe a static structure. The dynamism, the flow, the passage from past to future, none of that is in the equations. It emerges, somehow, at the level of human experience, but it is not a fundamental feature of the physics. This is sometimes called the problem of the now in physics and philosophy. It is genuinely puzzling. The physics does not contain a flowing present, but human experience clearly does. How do you get from one to the other? We will come back to this. Question 2. If the future also exists, does that mean everything is predetermined? This is a philosophically loaded question, and it deserves a careful answer. The block universe does imply that future events are, in some sense, already there in the structure of space-time. The words you will say tomorrow are already located at tomorrow's coordinates in the block, if the block universe is correct. But this does not necessarily mean that those events are causally determined in the way that old-fashioned determinism would have it. Quantum mechanics introduces a level of genuine indeterminacy into physics that is separate from the block universe question. Some interpretations of quantum mechanics are compatible with the block universe, and some are not, or not straightforwardly. This is an active area of research and genuine uncertainty at the frontier of physics. What we can say is that the block universe does not automatically make you a helpless automaton. Your choices, your deliberations, your experience of weighing options and deciding all of that is also in the block. The fact that your choice is located at a particular space-time coordinate does not make it less of a genuine choice, any more than the fact that a story is written down makes the events in it less of a genuine story. Question 3. If all moments are equally real, why do we remember the past but not the future? This is one of the deepest questions in the physics of time, and it leads us directly to one of the most important and underappreciated ideas in all of physics, the arrow of time. The laws of physics, not all of them, but nearly all of them are time-symmetric. They work equally well, run forward or backward. A video of two billiard balls colliding and bouncing apart is indistinguishable from the same video run in reverse. Both look like perfectly valid physics. A movie of the planets orbiting the sun, run backward, still looks like valid planetary motion. If you reverse the direction of time at the microscopic level, the fundamental laws would look the same. And yet, time has a direction. You remember the past and not the future. Eggs break, but do not unbreak. Heat flows from hot to cold, and not the reverse. The universe started in a state of extraordinarily low entropy, and has been moving toward higher entropy ever since. And that movement defines the direction of time. Why? If the laws are symmetric, why is there an arrow? This is what we are going to explore next. And the answer is stranger, and more beautiful, and more deeply connected to the block universe than you might expect. But first, there is something we need to deal with that is easy to gloss over, but too important to skip. Because so far, we have been talking about special relativity and the block universe in theoretical terms. Let us talk about the evidence. Section 4. Your clocks are already disagreeing. The proof. Here is a fact that should stop you in your tracks if you have not heard it before. The GPS network, the system of satellites that your phone uses to tell you where you are, that ships use to navigate, that airplanes use to land in fog, that emergency services use to route ambulances, does not work unless it corrects for time dilation. Time dilation is the phenomenon, predicted by both special and general relativity, by which time passes at different rates for observers, in different states of motion, or at different positions in a gravitational field. It is not a hypothetical effect. It is not something that only matters at exotic scales. It is something that must be corrected for, every single day, in the infrastructure of modern technology. Here is how large the effect is for GPS satellites. The satellites orbit at an altitude of about 20,000 kilometers, which means they are in weaker gravity than we are on the surface. According to general relativity, weaker gravity means time runs slightly faster. The satellite clocks gain about 45 microseconds per day relative to clocks on Earth due to this effect. Meanwhile, the satellites are moving at about 14,000 kilometers per hour relative to the Earth's surface. According to special relativity, motion slows time. The satellite clocks lose about 7 microseconds per day due to this effect. The net result is that GPS satellite clocks run fast by about 38 microseconds per day relative to clocks on the ground. That sounds tiny, but in GPS navigation, which depends on the precise timing of signals, 38 microseconds per day corresponds to a navigation error of roughly 11 kilometers per day. Uncorrected, GPS would be useless for navigation within hours of deployment. GPS works. GPS works accurately. Therefore, the relativistic time dilation is real, and it is being corrected for in real time, as you read this, in the satellites overhead. That is not theoretical. That is engineering. But let us go back earlier, to a more direct demonstration. In 1971, two physicists named Joseph Hafele and Richard Keating put atomic clocks on commercial airplanes and flew them around the world once eastward and once westward, while keeping identical clocks on the ground. When the airplanes landed, they compared the clocks. The results matched the predictions of relativity to within the measurement precision of the experiment. The clocks on the airplanes did not show the same time as the clocks on the ground. Time had genuinely passed at different rates. This experiment has been repeated many times with increasingly precise clocks. In 2010, physicists at the National Institute of Standards and Technology in Colorado demonstrated gravitational time dilation across a height difference of just 33 centimeters a foot. They elevated an aluminum clock by 1 foot and showed that it ran at a measurably different rate than an identical clock 1 foot lower. The effect was tiny. It would take 300 million years for the clocks to diverge by 1 second, but it was there, and it was exactly what general relativity predicted. Time is not universal. Time is not absolute. Time is a physical quantity that is affected by motion and gravity, and it passes at different rates in different parts of the universe, and we have measured this precisely and repeatedly and confirmed it beyond any reasonable doubt. Now, why does this matter for the block universe and the reality of the past? Because if time were universal and absolute, if there were a single cosmic clock that everyone shared, then you could at least construct a coherent picture of the present moment everywhere. You could say, right now, simultaneously, across all of space, this set of events is occurring, this other set has already occurred, and this third set has not happened yet. The present would be a global fact, but time is not universal. Different observers have different proper times, the time measured along their particular path through space-time, and those proper times do not synchronize into a global present. There is no moment that is now for the entire universe. This means that if you want to say the present is the only thing that exists, you immediately run into a problem. Present for whom? At whose rate of time? From whose frame of reference? The block universe does not have this problem. In the block universe, all events are simply events. space-time points, located at their coordinates, real whether anyone is currently experiencing them or not. The concept of the present is a local observer relative concept, not a universal one. And this is exactly what the physics of relativity supports. There is one more piece of evidence worth considering here, because it is so direct and so elegant that it deserves its own moment. In the early years of this century, physicists were studying a class of particles called muons. Muons are created in the upper atmosphere when cosmic rays, high-energy particles from space, collide with air molecules. Muons are unstable. They decay into other particles within about 2.2 microseconds of being created. The upper atmosphere is about 15 kilometers above the Earth's surface. At the speed of light, it takes about 50 microseconds to travel 15 kilometers. Muons travel at close to, but not quite the speed of light, say 98% of it. At that speed, it should take them about 51 microseconds to reach the ground, but they decay after 2.2 microseconds. So, by simple calculation, almost no muons should ever reach the surface. They arrive by the millions. The reason is time dilation. From our perspective on the ground, the muons' internal clocks are running slow because they are moving at high speed relative to us. Their 2 microsecond lifetime, as measured by their own proper time, corresponds to much longer in our reference frame. So they live long enough to reach the ground. From the muons' perspective, the situation is equivalent but looks different. The distance between the upper atmosphere and the ground is Lorentz contracted, shortened by the factor corresponding to its speed, so the distance it has to travel is much less than 15 kilometers, and it can complete the journey in its 2.2 microseconds. Both pictures are correct, both are real, and both confirm, in a concrete and measurable way, that time and space are not absolute quantities, but are relative to the observer, and that the four-dimensional structure of space-time is the correct framework for describing reality. The past is still there, not as a metaphor, as a location in a real geometric structure that has been confirmed by a century of experiments. The question is not whether it exists, the question is why you cannot reach it. And answering that question requires understanding something about time that most people have never thought about. Why, if the laws of physics are so nearly symmetric between past and future, does time have a direction at all? Section 5. The arrow problem. Why physics flows one way. Imagine you are watching a movie. In the movie, a cup of hot coffee sits on a table. Over the course of a few seconds, the coffee cools, losing heat to the air around it until it reaches room temperature. The steam dissipates. The warmth spreads. Now the movie runs in reverse. Room temperature air spontaneously heats a cool cup of coffee. Heat flows from colder to hotter. Steam spontaneously reforms and sinks back into the liquid. You would immediately know the movie was running backward. Not because you could point to a law of physics being violated. In fact, none of the fundamental laws of physics are technically violated by the reverse scenario at the microscopic level. Every single molecular collision in the reversed movie is individually valid, individually permitted by the laws of classical mechanics and electromagnetism. But the overall behavior heat flowing backward, entropy decreasing, looks wrong. It looks impossible. Why? This is the problem of the arrow of time, and it is one of the most profound and underappreciated puzzles in all of physics. Let us be precise about what makes it puzzling. The laws of physics, at least the classical ones, and very nearly all of the quantum ones, with one critical exception we will get to, are time reversal symmetric. If you take any physical process described by these laws and reverse the direction of time, you get another valid physical process. A planet orbiting a star in one direction is described by the same equations as a planet orbiting in the other direction. A particle collision is described by the same mathematics whether you run the clock forward or backward. The equations of motion do not have a preferred direction, and yet the universe clearly does. It has a past direction and a future direction. They are not equivalent. You can remember the past, but not the future. You can influence the future, but not the past. Entropy, the measure of disorder, of how spread out energy, is always increases. Processes are irreversible. Time flows. Where does this asymmetry come from, if the laws are symmetric? The answer, and this is a beautiful and somewhat vertiginous answer, is that it does not come primarily from the laws at all. It comes from the initial conditions of the universe. Here is the key idea. The laws of physics are time-symmetric. That means that for any low-entropy state of a system, the same laws that would let it evolve into a high-entropy state in the future would also let it evolve into a high-entropy state in the past if you reverse time. In other words, a low-entropy state is unstable in both temporal directions. It is statistically overwhelmingly likely to have come from a higher entropy state, just as it is overwhelmingly likely to evolve into one. Here is the puzzle. If low-entropy states are statistically unstable in both directions, why do we find ourselves in a universe where entropy was very low in the past and is increasing toward the future? Why is the past the low-entropy direction? The answer is because the universe started in an extremely low-entropy state. The Big Bang, or more precisely, the earliest state we can describe with our current physics, was a state of extraordinarily, almost incomprehensibly low entropy. Matter and energy were arranged in a way that was remarkably smooth, remarkably uniform, remarkably ordered, given the enormous number of possible arrangements the universe could have been in. The cosmologist Roger Penrose has tried to put a number on how unlikely this initial state was. He calculated the entropy of the universe's initial state and compared it to the entropy it would have if all the matter collapsed into black holes, which would be an extremely high entropy configuration. The ratio, roughly 1 in 10 to the power of 10 to the power of 123. That is not just a big number. It is a number that does not fit in the observable universe if you write out every digit, not even close. The universe started in an absurdly improbable state of low entropy, and because it started there, everything since has been moving toward higher entropy. That movement is what we experience as the flow of time. This is called the past hypothesis by philosophers of physics, the assumption, or the fact, that the early universe was in an extremely low entropy state, and it is this fact, not any asymmetry in the fundamental laws, that gives time its arrow. The implication is profound. The reason you can remember the past but not the future, the reason causes precede effects, the reason hot coffee cools and does not spontaneously heat up, all of this traces back to one fact. The universe began in an extraordinarily ordered state and has been relaxing toward disorder ever since. And that relaxation is the physical basis of the direction of time. Now, here is where this connects back to the block universe and the unreachability of the past. In the block universe, all moments exist, but the moments are not arranged arbitrarily. They are arranged in a structure defined by the laws of physics and the initial conditions. The low entropy beginning is at one end of the block. The high entropy future is at the other. And the internal structure of the block, the pattern of what is adjacent to what, which events can causally influence which other events, respects the arrow of time. You cannot travel to the past, not simply because it is in the wrong direction, but because the structure of the block itself prevents certain kinds of connections. The physical processes that would be required to send you back in time would all involve massive decreases in entropy, which are essentially impossible at the macroscopic scale given the statistics of a universe with our particular initial conditions. Think of it this way. The block universe is not like a stack of pancakes where you can just reach down and pick up an earlier one. It is more like a river delta, a complex network of channels where water flows in certain directions because of the overall slope of the land, not because each individual water molecule is prohibited from flowing uphill. Any individual water molecule could, in principle, move uphill in some microsecond scale collision. But the collective behavior, determined by the overwhelming statistics of the system, always flows toward the sea. You are made of billions upon billions of atoms. The probability of all of them simultaneously doing something that moves you backward through time, that decreases entropy by the enormous amount required to undo your own history, is not zero. It is just so close to zero that it will never, ever happen. Not in any length of time you can meaningfully contemplate. The past exists. The arrow points away from it. And the arrow is not arbitrary. It is anchored in the most improbable fact in the known universe, that the Big Bang was extraordinarily orderly. But wait, we said that the laws of physics are nearly all time-symmetric, with one critical exception. That exception is important. and it changes the picture in a way that most people do not know about. Section 6. The asymmetry hidden in the laws themselves. For a long time, physicists assumed that the laws of physics were completely symmetric between past and future, that time reversal symmetry was exact and universal. The arrow of time came from statistics and initial conditions, as we just described, but the underlying laws themselves were perfectly neutral. In 1964, a pair of physicists at Brookhaven National Laboratory, named James Cronin and Val Fitch, were doing an experiment that, on the surface, had nothing to do with the arrow of time. They were studying a class of particles called kaons, exotic particles produced in high-energy collisions, and they found something unexpected. Kaons are governed by the weak nuclear force, and they found that kaons behave differently depending on whether they were decaying in a process that matched the time-reversed version. The violation was tiny, only a fraction of a percent, but it was there, and it was real, and it was exactly reproducible. This phenomenon is called CP violation, and it means that the laws of physics are not, in fact, perfectly symmetric under time reversal. The weak force has a slight preference for one direction over the other. Cronin and Fitch won the Nobel Prize in Physics in 1980 for this discovery. It was one of the most surprising results in 20th century physics, not because the violation was large, but because it existed at all. The implications take a moment to absorb. If CP violation exists, if the laws of physics have even a small intrinsic asymmetry between past and future, then the arrow of time is not purely a statistical artifact of initial conditions. It is, at some level, built into the laws themselves. This has been confirmed and extended since Cronin and Fitch. In the 1990s and 2000s, experiments at CERN and at the Stanford Linear Accelerator Center studied a different class of particles, the B mesons, and found CP violation in those systems as well. In 1998, an experiment called CPLEAR at CERN directly measured time reversal violation in kaon decay, not just inferring it from CP violation, but measuring it directly by comparing the rate of a process to the rate of its exact time reverse. The asymmetry was there, and in 2012, the Babar experiment at Stanford published what was arguably the most direct measurement of time reversal violation ever made, directly comparing decay processes and their time-reversed counterparts in B meson systems and finding a clear, statistically definitive asymmetry. The universe, at its most fundamental level, does not treat past and future equally. The laws of physics have a directional bias. It is small, you would not notice it in everyday experience, but it is real. Now, here is a subtle and important point. The CP violation we have measured is far too small to explain the thermodynamic arrow of time by itself. The overwhelming practical reason coffee cools and eggs break is still statistics and the initial conditions of the universe. The tiny asymmetry in kaon decay does not directly cause cups to shatter rather than reassemble. The scales are completely different, but the existence of this asymmetry suggests something deeper and philosophically important. The asymmetry of time is not just an illusion created by our vantage point. It is not purely a story we tell ourselves because we happen to be located at a low entropy moment in cosmic history. The laws themselves have a directional arrow. The universe, at its deepest level, knows which way is forward. There is a stronger and more speculative version of this argument. In the very early universe, in the first fractions of a second after the Big Bang, when temperatures were so extreme that particles and antiparticles were created in roughly equal numbers, CP violation played a crucial role. Our universe contains matter, but very little antimatter. If the laws were perfectly symmetric, matter and antimatter would have been produced in exactly equal quantities, and they would have annihilated each other completely, leaving nothing but radiation. The fact that anything exists, any matter, any stars, any planets, any people asking questions about time, is because CP violation gave matter a very slight edge over antimatter in those early moments. The asymmetry of time, written in the decay of exotic particles, is why anything exists at all. We are here because the laws of physics are not perfectly time-symmetric. That is not a small fact. That is perhaps one of the most important structural facts about the universe. This deepens the picture of why the past is unreachable. It is not merely that the past is in the wrong statistical direction. It is that the laws of physics themselves have an orientation. The universe has a grain. The way wood has a grain, it is much easier to cut with it than against it. Moving into the past would mean moving against the grain of the laws themselves. And yet the block universe still says the past is there, still says those coordinates exist. And some of the most creative minds in physics have asked, what if you could find a route that does not require going against the grain? What if there is some structural feature of space-time itself that could, in principle, connect different moments? This is where things get very strange. Section 7. The Quantum Strangeness. Wheeler's Delayed Choice. Before we go to curved space-time and closed time-like curves and the most exotic structures in general relativity, we need to spend a little time in quantum mechanics. Because quantum mechanics raises a question about time that is, in some ways, even stranger than anything in relativity, the question is, do causes always precede effects? We assume they do. Causality, the principle that effects cannot precede their causes, is so deeply embedded in our understanding of physics that it is hard to even imagine it being violated. And in practice, for large-scale systems, it is not violated. The future does not influence the past. Effects follow causes. This is the basis of everything. But quantum mechanics operates at the microscopic level, and at that level, things are not so clean. Consider an experiment proposed by the physicist John Archibald Wheeler in 1978. Wheeler was one of the most creative theoretical physicists of the 20th century. He coined the term black hole. He worked on the Manhattan Project, and then spent his later career thinking deeply about the nature of quantum reality and time. And, in 1978, he proposed a thought experiment that went to the heart of something deeply unsettling about quantum mechanics. Here is the setup. You fire a single photon, a single particle of light, at a half-silvered mirror. A half-silvered mirror reflects half of incident light and transmits half. When a single photon hits it, the quantum mechanical description is that the photon goes both ways simultaneously. It enters a superposition of reflected and transmitted states. It is in both paths at once. Now you bring those two paths back together so they can interfere. This is a standard interferometer setup. If you measure which path the photon took before it recombines, you get a particle-like result. It went one way or the other, and the interference pattern disappears. If you do not measure which path it took, you get a wave-like result. It went both ways, and the paths interfere with each other. Here is Wheeler's twist. What if you wait until after the photon has passed the first half-silvered mirror, after it has committed to being in both paths, and then decide whether to insert the detection equipment that would reveal which path it took? The result, which has been confirmed experimentally multiple times since Wheeler proposed it, is deeply strange. The photon's behavior, whether it acts as a wave going both ways or a particle going one way, is determined by the measurement you decide to make after the photon has already passed the first mirror. The future measurement influences, or at least correlates with, the photon's past behavior. Wheeler himself was careful about how to phrase this. He did not say that the future causes the past. He said that, at the quantum level, there is something fundamentally retrocausal seeming about the relationship between observations and events. The notion that the photon had a definite path before the measurement is not supportable. The measurement made in the future, relative to the photon's passage through the mirror, participates in determining what the photon did. This has been extended in increasingly dramatic ways. In 2007, a team of physicists performed a cosmic-scale version of Wheeler's experiment, using quasars as light sources. The choice of measurement was made on Earth, and the photon's path extended across billions of light-years. The retrocausal seeming correlation persisted at cosmological scales. Now, what does this mean for the block universe and the arrow of time? It means that quantum mechanics introduces a kind of non-locality and non-classical temporality that makes the simple picture causes at earlier times produce effects at later times. Full stop, more complicated at the microscopic level. It does not allow actual signals to travel backward in time. You cannot use quantum retrocausation to send information into the past because the correlations only reveal themselves statistically after the fact. The no-communication theorem in quantum mechanics is solid. But it does suggest that the block universe picture, where all events are simply there, and the distinction between past and future is less fundamental than it seems, finds a natural partner in quantum mechanics. The Wheeler delayed choice experiment is not proof of the block universe, but it is consistent with a universe where time is less of a strict one-way highway than our intuitions suggest. There is a deeper layer to the quantum story, and it concerns what happens to the quantum description of the universe when you try to combine it with general relativity. General relativity is a theory of curved spacetime. Quantum field theory, which is our best framework for describing particles and forces at the quantum level, operates on a flat background spacetime. Reconciling these two theories, producing a theory of quantum gravity, is the deepest open problem in theoretical physics. And in the attempts to do so, some very strange things happen to time. One of the most striking is something called the Wheeler-DeWitt equation, which is a candidate for the fundamental equation of quantum gravity. When physicists Carlo Rovelli, Bryce DeWitt, John Wheeler, and others worked on this equation, they discovered something alarming. The equation has no time variable. Time disappears from the fundamental description. This is known, informally, as the problem of time in quantum gravity. If you try to write down the most fundamental equation of the universe, time drops out. The universe, at its deepest level, may not evolve in time. It may just be. This is an active and unresolved research area, and no one fully understands what to make of it. But it is a remarkable convergence. General relativity points to a block universe where all times are equally real. Quantum gravity hints at a universe where time is not fundamental at all. And quantum mechanics shows that even at the level of individual particles, the distinction between past and future is less clean than it appears. Time, the more you examine it, becomes less and less like a river, and more like a human projection onto a structure that does not, at the deepest level, flow at all. But we have been circling around the most obvious question long enough. People who have heard about the block universe, about relativity, about the reality of the past, the first thing they want to know is, what about time travel? What about going back? So let us address that directly. And let us be careful to distinguish between the different kinds of impossibility involved, because they are not all the same. Section 8, Can you go back? The geometry of impossible journeys. The block universe says the past exists, so why can't you just go there? This question deserves a serious answer, because the obstacles to backward time travel are not all the same kind of thing, and understanding the differences between them is part of understanding what time actually is. Let us start with general relativity, because general relativity is the most permissive of the relevant theories on this question, and even here, the obstacles are severe. In general relativity, space-time is curved by the presence of mass and energy. Gravity is not a force in Einstein's picture. It is the curvature of space-time itself. Objects in freefall, including the Earth orbiting the Sun, and you sitting in a chair, follow paths called geodesics through curved space-time, and the shape of space-time determines which paths are possible. In the space-time of ordinary experience, the possible paths through the block are constrained by a structure called the light cone. At every point in space-time, you can draw a cone that represents the boundary of what can be causally connected to that point. Events in the future light cone can be influenced by what happens here. Events in the past light cone could have influenced what happens here. Events outside the light cone are causally disconnected. Nothing can travel faster than light, so nothing can get outside its own light cone. For a backward time journey, you would need a path through space-time that eventually loops back to earlier coordinates, a closed time-like curve, or CTC. A closed time-like curve is a path through space-time that is everywhere within the light cone, but that eventually returns to its own starting point. If you followed a closed time-like curve, you would travel normally, always at less than the speed of light, always in your local future direction, but you would end up in your own past. The remarkable thing is that general relativity does not, in principle, forbid closed time-like curves. In fact, the very first exact solution to Einstein's field equations to contain closed time-like curves was found by Kurt Gödel, the logician of incompleteness theorem, FAME, in 1949. Gödel found a solution describing a rotating universe in which closed time-like curves exist everywhere. In that universe, you could travel anywhere in time simply by following a large enough loop through space. Our universe does not appear to be the Gödel universe. It is not rotating in the relevant way. But the Gödel solution demonstrated that general relativity is at least not categorically inconsistent with closed time-like curves. Other solutions have been found since, solutions involving wormholes, solutions involving infinitely long rotating cylinders, solutions involving regions of exotic matter with negative energy density. So, is backward time travel possible in principle, within the framework of general relativity? The answer has to be maybe, but with enormous caveats. Let us take the wormhole proposal, which is the most seriously discussed in the scientific literature. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical structure in spacetime, a shortcut connecting two distant regions of space. Wormholes arise as valid solutions to Einstein's equations. They were first discussed by Einstein and Nathan Rosen in 1935, though originally in the context of trying to model particles geometrically, not as objects for time travel. In 1988, the physicists Kip Thorne, who would later win the Nobel Prize for his role in the detection of gravitational waves, and Michael Morris, published a serious scientific paper analyzing whether wormholes could be stabilized and used for interstellar travel. They found that to keep a wormhole open, you would need to thread it with something called exotic matter, matter with negative energy density, which would produce a repulsive effect to counteract the tendency of the wormhole to collapse. Exotic matter is not ruled out by physics. The Casimir effect, a measurable force between closely spaced metal plates in vacuum caused by quantum fluctuations, involves regions of negative energy density. But the amount of exotic matter required to stabilize a traversable wormhole at any useful size is estimated to be astronomically, probably impossibly, large. Thorne and his colleagues further showed that if you had a traversable wormhole and moved one mouth of it relative to the other at high speed, the time dilation between the two mouths would produce a difference in elapsed time, and this difference could, in principle, be used to travel backward in time. If you moved one mouth of the wormhole through a round trip at relativistic speed, and then stepped through the wormhole from the slower aging mouth to the faster aging mouth, you could emerge at an earlier time. This is, in a sense, the most physically serious time machine ever proposed. Thorne is not a crank. He is one of the greatest physicists of the 20th century, and his analysis showed that if exotic matter exists in the required quantities, if a traversable wormhole can be created and stabilized, then in principle, backward time travel is permitted by general relativity. But notice how many ifs are in that sentence. The first if is the exotic matter. The Casimir effect gives us microscopic regions of negative energy density. A traversable wormhole requires macroscopic amounts, perhaps the mass energy equivalent of a large star, arranged in exactly the right configuration. There is no known mechanism for doing this. The second if is even more fundamental, creating a wormhole in the first place. Wormholes appear as solutions to Einstein's equations, but that does not mean nature creates them. We have never observed a wormhole. There is no observational evidence that wormholes exist anywhere in the universe. To create one, you would presumably need to manipulate space-time at the Planck scale, at energies so extreme that they are unlikely to be achievable by any civilization at any point in history. The third obstacle, and this is one that operates at a completely different level, was identified by Stephen Hawking in 1992. Hawking showed or argued, because his result was not a rigorous mathematical proof, that quantum mechanics might prevent the formation of closed time-like curves. His argument was called the chronology protection conjecture. The idea is this: any spacetime that is on the verge of developing a closed time-like curve, where the light cones are almost about to tilt into a loop, becomes a place where virtual particles from quantum field theory begin to pile up and amplify. The vacuum energy diverges. The energy density at what would be the edge of the time machine grows without bound, and this diverging energy would destroy the structure before it could form a closed time-like curve. In other words, quantum mechanics has a self-correcting mechanism that prevents time machines from forming. Hawking famously quipped that this was strong experimental evidence for the chronology protection conjecture, because if closed time-like curves were possible, we would expect to be overrun by tourists from the future. And we are not. The conjecture has not been proven rigorously. It relies on approximations that might not be valid near actual would-be time machine boundaries. And in 2003, Some physicists argued there are cases where the vacuum energy does not diverge. The question is genuinely open. But the picture that emerges is clear. Even within the most permissive physical framework, we have general relativity. Without quantum corrections, the construction of a time machine faces obstacles that are not merely technological, but potentially fundamental. And when you add quantum mechanics to the picture, there is a strong argument that nature actively prevents these structures from forming. The past is real. The path back is blocked. But the blocking is not simple. It is not one wall. It is layer upon layer of physical constraint, each one deeper and more fundamental than the last. And there is one more layer we have not discussed yet. What would happen if you did go back? What does physics say about the consequences? Section 9. The Novikov Principle. What if the past defends itself? Let us say, for the sake of argument, that everything worked. You built the wormhole. You stabilized it. The vacuum energy did not diverge and destroy it. You stepped through. You are in the past. Now what? The first thing you notice is that this situation is apparently riddled with paradoxes. The grandfather paradox is the most famous. You travel to the past and kill your own grandfather before he has children. As a result, you are never born. As a result, you never travel back in time. As a result, you never kill your grandfather. As a result, you are born. As a result, you travel back in time and kill your grandfather, and so on, forever, in a loop with no resolution. Paradoxes like this are often treated as simple arguments against the possibility of backward time travel. If it leads to contradiction, it must be impossible. But the physicist Igor Dmitrievich Novikov, and independently, several other physicists and philosophers proposed a more interesting response. What if the past does not allow paradoxes? What if the structure of space-time is such that, on any closed time-like curve, only self-consistent histories are physically possible? This is the Novikov self-consistency principle, and it is more interesting than it might first appear. Here is the intuition. On a closed time-like curve, events are causally connected in a loop. What you do in the past influences what happens in the present, which sent you to the past, which determines what you do in the past. It is a closed causal loop. And if the laws of physics are to be satisfied everywhere along the loop must be consistent. You cannot do anything in the past that would prevent you from being there in the first place. Novikov's principle says that when you analyze the physics of what would happen on a closed time-like curve, the only trajectories that survive are the self-consistent ones. Paradoxical trajectories, trajectories that would create contradictions, have zero probability. Not low probability, exactly zero. This sounds like it might be a cop-out. The universe just won't let you make a paradox. But there is actual mathematical content here. Physicist Joe Polchinski and colleagues studied this in the early 1990s by asking about a simpler scenario: a billiard ball that travels through a wormhole and comes out in the past in time to collide with itself, deflecting itself so that it never enters the wormhole. Is this consistent? Polchinski found that the obvious inconsistent trajectory: ball enters wormhole, ball deflects itself, ball never enters wormhole. Paradox does indeed seem paradoxical. But when he analyzed all possible trajectories using the mathematics of classical mechanics, he found that there are always self-consistent solutions. The ball comes out of the wormhole at a slightly different angle, hits itself a glancing blow rather than a deflecting one, and the result is a trajectory that is consistent. The ball enters the wormhole with exactly the right initial conditions to produce that glancing blow. The paradox resolves not by prohibition, but by the mathematics selecting only consistent histories. The resolution of the grandfather paradox under the Novikov principle would be something like, you can travel to the past and try to kill your grandfather, but something will always prevent it, not because some external agency intervenes, but because the physics will only permit the self-consistent solution. Your hand will tremble, the weapon will misfire. You will not be there at the right moment. Whatever happens, you will fail, because in the actual history of the universe, you did not kill your grandfather, and no matter what, that history must be consistent. The philosopher David Lewis put it this way: what you cannot do in the past is anything that did not happen. You are as capable of doing it as you are capable of doing anything else. But in fact, you will fail, because the physical trajectory of the universe must be self-consistent. This is a genuinely profound idea. It means that the past is not just inaccessible, it is in a certain sense defended. Not by an external force, but by the self-consistency requirements of physics itself. The past is what it is. Whatever happened, happened. And any closed causal loop must be consistent with what actually happened. Stephen Hawking, in his paper on the chronology protection conjecture, was skeptical of the Novikov principle as a general solution. His point was that the Novikov principle tells you that self-consistent solutions always exist in principle, but it does not tell you how the physics selects the consistent solution from the inconsistent ones. In quantum mechanics, probabilities are calculated before the fact, not constrained by consistency conditions after the fact. A quantum treatment of the billiard ball problem does not obviously give the same neat result. Later work by Kip Thorne and others suggested that in quantum mechanics, the situation is more complex. On closed time-like curves, the standard rules of quantum mechanics need to be modified, and different modifications give different results. Some modifications allow consistent evolution on CTCs. Others do not. The question of which modification, if any, is physically correct is not resolved. But the Novikov principle illuminates something important about the relationship between time travel and the reality of the past. If the past exists in the block universe, if all moments are real and located at their coordinates, then any time traveler is simply another element of that block. They do not create new histories. They are already part of the history that existed. Their presence, their actions, their interference, all of it is already there, in the block, as part of what actually happened. The past does not need to be changed by a time traveler. It was always the history that included that time traveler. This is not time travel in the Hollywood sense, going back and fixing things, altering outcomes, creating alternate timelines. In the Novikov picture, there are no alternate timelines. There is one block, one history, and any time traveler is simply part of that one history, traveling a closed loop within it. It is a more subtle and philosophically richer concept than the popular image of time travel. And it connects back to everything we have been building: the block universe, the reality of the past, the constraints that prevent paradox, the way the structure of space-time enforces self-consistency. But let us step back from the edge cases and exotic scenarios and come back to the main question, which is not really about time machines. Most of us are not building wormholes. Most of us are not troubled by the grandfather paradox, in a practical sense. What most of us are troubled by is the loss of ordinary moments. The way a day passes and is gone, the way years accumulate and slip behind. The way the people and places and ordinary perfect afternoons of the past are unreachable, not because of exotic space-time geometry, but because of something more fundamental, because of the way time and memory and entropy work together to make the present moment feel uniquely alive, and everything before it feel permanently past. Why are you locked out? Not the exotic version, the real version. The one you feel in your bones every time you try to remember something that is already fading. Section 10. Why you are locked out. The full architecture of impossibility. We have covered a lot of ground. Let us now bring it together into a unified picture of why, even though the past exists, you cannot reach it. There are, it turns out, several distinct layers of reason. They operate at different levels of physical description, and they reinforce each other. Understanding all of them gives you a much richer picture of what time actually is. Layer 1. The thermodynamic barrier. This is the most immediately powerful reason. You are a macroscopic physical system. You are made of something on the order of 700 trillion atoms. For you to travel backward through time to retrace your world line from now to some earlier point would require the entropy of your body and the entropy of everything that has interacted with your body to decrease by an enormous amount. The coffee you drank this morning would need to undrink itself. The words you spoke would need to unspeak themselves. The energy you have metabolized would need to be unmetabolized, rebuilt from heat back into structured chemical compounds. Each of these processes individually has an infinitesimally small probability of spontaneous reversal. Together, the probability is so close to zero that it is effectively impossible, not just for your lifetime, not just for the age of the universe, but for any number of universe lifetimes you might care to name. This is not a technological obstacle, it is a statistical one. There is no machine that can make entropy decrease in a closed system. The second law of thermodynamics is not a law in the sense of being imposed by external authority. It is a statistical fact, the most probable outcome, overwhelmingly dominant at macroscopic scales. The thermodynamic barrier alone means that no macroscopic system can travel to the past, regardless of what the space-time geometry permits. Layer 2. The causal structure of space-time. Even setting aside thermodynamics, even imagining, as a thought experiment, that you could somehow reverse all the entropy changes involved, you still have to navigate the structure of space-time itself. As we discussed, the light cone at every point in space-time constrains which events can be connected. Traveling to your past would require following a path through space-time that exits your forward light cone and re-enters your backward light cone. Nothing with mass can travel faster than light, so you cannot exit your light cone by going fast. You would need the space-time itself to curve in a way that creates a closed time-like curve. For that to happen near you, near ordinary matter, at ordinary densities, you would need energy densities and curvatures that are not available in nature except at the extreme conditions of black hole formation and the very early universe. Normal space-time is locally flat to extremely high precision. There are no closed time-like curves in your neighborhood. None. This is a geometric obstacle, separate from the thermodynamic one. Even if entropy were not an issue, the geometry of your local space-time does not permit a path to the past. Layer 3. The quantum mechanical prohibition. As Stephen Hawking argued in the chronology protection conjecture, even in regions of space-time where the curvature is trying to form a closed time-like curve, quantum field theory produces a diverging vacuum energy that would destroy the structure before it could form. The quantum vacuum, the ground state of quantum fields, is not simply empty. It is filled with fluctuating virtual particles, and near a forming time machine, these fluctuations amplify without bound. This is not a classical effect. It is not about energy densities achievable with ordinary matter. It is about the quantum properties of empty space, which turn out to be violently opposed to the formation of time machines. The vacuum itself destroys them. Layer 4. The informational barrier. There is a fourth reason that is less often discussed, but deeply important. It concerns information. Going to the past is not just about moving your body to an earlier set of space-time coordinates. It is about carrying information from the future into the past. You would know things that no one in the past knows because you have experienced events that have not yet happened from their perspective. This creates a problem at the level of information theory. In a consistent block universe, information must be conserved. The total information in the system is constant, and it cannot be created or destroyed. Information traveling from the future to the past would create a closed causal loop of information, a loop in which information appears to have no ultimate source because it keeps circling around, an idea that you bring from the future to the past that then gets developed in the past and eventually leads to you having the idea has no original author. This is sometimes called a bootstrap paradox. Some physicists think bootstrap paradoxes are self-consistent and therefore permissible. Others think they represent a genuine violation of something important about causality and information. The discussion is ongoing. But at a minimum, closed loops of information are deeply uncomfortable in a physical framework that takes causality seriously. Layer 5. The absence of time travelers. This is perhaps the most practical argument, and it was made most memorably by Stephen Hawking. If backward time travel were possible, we would expect to see visitors from the future, perhaps not tourists arriving at the airport, but evidence, signals, influence. If closed time-like curves exist and are accessible, then observers from later times would be able to send information to earlier times. And in a universe with intelligent beings making observations for billions of years, we would expect to see some trace of this. We do not. The past, as far as we can tell, is entirely free of contamination from the future. No signals from future observers have been detected. No closed loops of information are known to exist. The causal structure of the universe, as we observe it, is clean. This is not a mathematical argument, but it is a strong empirical one. And Hawking took it seriously as evidence that closed time-like curves, if they can exist at all, are inaccessible in practice. Taken together, these 5 layers of impossibility constitute what we might call the full architecture of the past's unreachability. The past is real. It exists in the block, at its coordinates, as permanent as any other location in 4-dimensional spacetime. But the path to it is blocked not once, but 5 times, at 5 different levels of physical description, from the microscopic statistics of thermodynamics, to the large-scale geometry of spacetime, to the quantum properties of the vacuum. The universe has built a wall. It built the wall, not with a single stone, but with 5 different materials, each independently sufficient to prevent passage, all working together. You are locked out. Not because the past is gone, but because the architecture of time is such that even permanent things can be unreachable. And that is a profound thought that deserves to be sat with, because there is something in it that is not quite comfort and not quite grief, something stranger and more interesting than either. Section 11. The strange comfort of a universe that forgets nothing. Let us set aside the physics for a moment, not discard it, but let it settle into the background and think about what it actually means at a human level to live in a universe where the past is permanent. You have experienced moments that you cannot return to. Everyone has. There are conversations that are over. There are people who are gone. There are days that passed without you fully appreciating them. Days that you would give almost anything to be inside again. Not to change them, just to be there. Just to feel that particular light, hear that particular voice, be that particular version of yourself in that particular moment. The ordinary human response to this is something between grief and nostalgia and a low-grade existential unease. The past is gone. You cannot get it back. Time is a thief, and what it takes, it never returns. But the physics says something different. The physics says that every one of those moments is, in the most literal sense, still there. Not metaphorically preserved in memory, not spiritually conserved in some non-physical realm, but physically, geometrically, actually located at coordinates in the 4-dimensional structure of the universe. The afternoon you are thinking of, whatever your particular afternoon is, whatever your particular irreplaceable moment is, at those coordinates right now. It is as real as this moment. It has not been erased. The universe does not erase. The Austrian physicist Erwin Schrödinger, of the famous cat, wrote late in his life about time and memory and physics in terms that feel almost more like poetry than physics, but that are entirely consistent with what we have been discussing. He described the present moment as a sharp knife edge moving through time and suggested that the feeling of loss we associate with the past is not evidence that the past is gone, but evidence that we are moving through it. We are not standing still while the river flows past us. We are the river moving. What is behind us is not absent. We are simply no longer there. This reframing, small as it might sound, changes something significant about how the loss of the past feels. The past is not a box of broken things. It is a location you have left. It exists as surely as a city you once lived in that still stands on its corner of the map, waiting, lit from inside with all its ordinary life, even though you are no longer walking its streets. The physicist Julian Barbour has spent decades developing a picture of physics in which time does not flow at all, in which the universe is simply a static 4-dimensional structure, fully present, with no flowing present and no genuine passage of time. Barbour calls each moment a now, a 3-dimensional configuration of the universe, and argues that all nows are equally real and eternal. In his picture, what we experience as the passage of time is a consequence of the way our memories are structured, not a feature of time itself. Barbour's view is controversial, even among physicists sympathetic to the block universe. But it illuminates something important. The question of what it would mean for the past to truly not exist is harder than it looks. And the question of what it means for the past to genuinely exist, even if unreachably, is more emotionally and practically significant than most people realize. Here is one way to think about it. You know that the city of Rome exists. You have not been there today. You cannot get there today. But knowing that it exists, knowing that it is real, that its buildings stand, that people are walking through it right now, is different from knowing that it has been destroyed. The existence of places you cannot reach is a different kind of fact from their non-existence. The same is true of the past. Every moment that has ever happened is somewhere in the block. It is not waiting for you. It does not have an experience of being waded through, but it is there. And knowing it is there is a different kind of fact from believing it is gone. There is also something important to say about legacy, about the way moments continue to influence the present even after they are in the past. In the block universe, the causal structure is real. The influence of past events on future events is not eliminated by the passage of time. The photons that left a star 10,000 years ago are still traveling. The words said in a particular conversation, the decisions made on a particular afternoon, the tiny choices that shifted the course of a life, all of these are woven into the structure of the block, influencing the future with the same permanence that the past itself has. You cannot return to the past, but the past is not passive. It is not dead. It is the foundation of everything that comes after it. And in that sense, it is enormously, structurally present in every moment. The universe does not forget. It cannot forget. Forgetting would require erasing, and the block universe does not erase. Every event that has occurred is encoded in the structure of space-time, and its effects ripple forward through every subsequent moment. The second law of thermodynamics ensures that information about the past is diluted, spread out, harder and harder to reconstruct, but it is never gone. It is there, distributed through the system, as real and permanent as the block itself. This is why physicists take seriously the idea that, in principle, a sufficiently precise observer with sufficient information could reconstruct the state of the universe at any past moment. Not in practice, the information is too diffuse, too diluted, spread across too many degrees of freedom. But in principle, the past is recoverable because it was never destroyed. The universe forgets nothing. We forget everything. And the gap between those two facts is the human experience of time. There is one more thing worth saying in this section, and it is something that the physics of time suggests about the way we relate to our own lives. You are, right now, creating the permanent past. The present moment, this one, right now, is in the process of becoming a location in the block. It will be there. It will not move. It will not fade. The light from this moment will travel outward through the universe for billions of years, and the space-time coordinates of right now will remain what they are for as long as space-time coordinates exist. What you do in this moment is permanent in a way that nothing can undo. Not time, not entropy, not distance, not the heat death of the universe. The fact of this moment will always have been. That is not a small thing, and physics, strange as it is the reason to believe it. Section 12, what physics has actually found. The full synthesis. We have come a long way. Let us bring everything together, slowly and clearly, because the full picture is extraordinary, and it deserves to be held whole. Here is what we have learned. Newton's picture of time absolute, universal, the same everywhere and for everyone, flowing at a steady rate from past to future, is wrong. Not approximately wrong, not wrong at the edges, wrong in its foundations. Time is not absolute. Time is not universal. Time is a dimension of a four-dimensional structure called space-time, and it is affected by motion and gravity. Different observers measure time differently, and both are correct. This is not a theoretical abstraction. It is measured every day in GPS satellites, in atomic clocks, in muon decay. It is the most tested prediction of the most tested theory in the history of physics. The most natural consequence of this, the consequence that falls out of the mathematics without any additional assumptions, is the block universe. The view that all moments in time are equally real, that the past and future exist with the same ontological status as the present, that there is no universal now, and therefore no coherent way to say that only the present is real. This is not fringe physics. It is not a minority view. The majority of physicists who have thought carefully about the metaphysics of time hold a view consistent with the block universe, or hold that our evidence most strongly supports it. The past exists, not as memory, not as record, not as potential reconstruction, but as actual physical fact. Your childhood exists at its space-time coordinates. Every moment you have ever lived exists at its coordinates. Every moment that will ever happen, if the block universe is fully correct, exists at its future coordinates, and yet you cannot go back. The reasons are multiple, overlapping, and operate at different levels of physical description. At the statistical level, you are a macroscopic object made of an astronomically large number of atoms. The entropy required to reverse your trajectory through time is so enormous that spontaneous reversal will never occur in any time you can contemplate. At the geometric level, the space-time around you is locally flat and contains no closed time-like curves. The structure of space-time in your neighborhood does not permit a path from your present location to any past location. The light cone is a one-way structure, and you are inside it. At the quantum level, the vacuum energy of quantum fields diverges near any region of space-time that tries to form a time machine. Hawking's chronology protection conjecture, while not rigorously proven, provides strong theoretical evidence that quantum mechanics actively prevents the formation of closed time-like curves, and the empirical absence of time travelers from the future provides practical support for this view. At the informational level, a journey to the past would require closed causal loops of information, bootstrap paradoxes, in which information has no original source. And while these are not strictly forbidden by any known law, they are deeply problematic for any causal account of physics. At the empirical level, the past is clean. There are no signals from the future in the historical record. There is no evidence of interference from later times. The universe, as far as we can observe it, has a clean, consistent causal structure in which the future does not influence the past, layer upon layer upon layer. The past is real, and the path back is blocked in every direction at once. Now let us ask the deeper question that all of this has been building toward. What does it mean for a moment to exist permanently if experiencing it is confined to the moment itself? Here is one answer. It means that existence and experience are not the same thing. Your experience of this moment is confined to this moment, but the existence of this moment is not. The existence of this moment is permanent, geometrically encoded in the structure of space-time, beyond the reach of entropy, beyond the reach of time, beyond the reach of anything at all. There is a philosophical tradition going back at least to Heraclitus, who said, "You cannot step into the same river twice," that treats the impermanence of experience as the fundamental fact about time. Moments pass, things change, nothing lasts. This tradition tends to produce a certain flavor of melancholy about time. The best moments of your life are the ones most worth mourning, because they are gone, and they are gone completely. The block universe inverts this. Moments do not pass in the sense of ceasing to exist. They pass in the sense that your experience moves on from them, but they remain. The best moments of your life are not gone. They are located. They are there, in the structure of the universe, as real as anything has ever been. You are simply not there with them anymore. You are here, somewhere else in the block, looking back at them from a distance that cannot be traversed. The grief does not disappear, but its character changes. You are not mourning the destruction of something. You are mourning the distance from something that still exists, and the distance is real. The layers of impossibility are real. The thermodynamics and the geometry and the quantum mechanics are all real obstacles. You cannot go back. Not even in principle, not even with infinite technology, not even with a complete understanding of every law of physics, because the obstacles are not technological, they are structural. They are built into the architecture of a universe that has time at its heart. But here is what the physics has found, and it is worth saying clearly and without mystification. The universe is four-dimensional. All moments are equally real. The past does not disappear. It occupies permanent coordinates in space-time. The flow of time is an emergent phenomenon, arising from the extraordinarily low entropy of the universe's beginning, amplified by statistical processes at every scale, and experienced by beings like us as the sensation of being carried forward through a structure that does not itself move. The laws of physics are nearly but not perfectly symmetric between past and future. The slight asymmetry found in the decay of exotic particles like kaons and B mesons is the reason matter exists at all. The universe chose a direction at the deepest level of its laws, and that choice is why stars and planets and people exist rather than nothing. Quantum mechanics, when pushed to its limits, suggests that time may not be fundamental at all, that the universe at the deepest level is a timeless structure. and time emerges in a way that physics does not yet fully understand. The problem of time in quantum gravity is one of the hardest open problems in theoretical physics, and its resolution, whatever it turns out to be, will almost certainly deepen and enrich the picture we have been building. And you specifically, watching this, wherever you are a physical process embedded in this structure. Your experience of the present moment is real. Your memory of the past is real. Your uncertainty about the future is real. All of these are features of being a complex physical system moving through a four-dimensional block, not features of time itself. The moments you have lost are not destroyed. They are behind you, in the block, as permanent as the laws that govern them. And the moments you will live are ahead of you, with equal permanence, equally real in the structure of space-time. Though whether the future is truly as fixed as the past is a question that quantum mechanics has not yet settled, and may never settle completely. What we can say is this: the universe is astonishing. The question of where the past goes has an answer that is not comforting in the simple sense. It does not give you your lost moments back, but it is comforting in a deeper sense. Nothing is wasted. Nothing is deleted. The universe has been building a permanent record of itself since the beginning, one moment at a time, and every entry in that record is as real as the cosmos that contains it. You cannot go back. But the past was always there, and it will always have been. That is what physics has found, and it is one of the most quietly magnificent things that science has ever told us about what it means to be alive in time. Addendum 1. The present moment. An illusion or the only reality? We have spoken throughout this video as though the present moment is simply one moment among many in the block, as though now is just a coordinate, no more special than any other point in four-dimensional space-time. And from the physics, this is correct. From the point of view of the equations, there is nothing special about now. But your experience of now feels overwhelmingly special. It feels like the only thing that is directly real. Everything else is memory or anticipation, inference or imagination. Only now is given. And this feels like it ought to be evidence for something, perhaps for presentism, the view that only the present is real. Perhaps for some physical process that generates the felt specialness of the present. What is the present moment in physics? The honest answer is that physics does not have a fully satisfactory account of this. The present moment, the specious present, as psychologists call the roughly 3-second window of time that we experience as now, is a feature of conscious experience, and consciousness itself is not well understood at the physical level. We know that the experience of now requires some integration of neural processes over a short time window. We know that different sensory inputs are delayed differently. What you see and what you hear arrive at your brain with slightly different lags, and your brain corrects for this to produce a coherent experience of simultaneous events. We know that the experience of time passing is related to the rate at which memory is formed. But none of this explains why there is an experience of now at all, rather than just a series of moments, with no one home to experience any of them. This is part of the hard problem of consciousness, and it is not solved. What we can say is that the physics points strongly toward the block universe interpretation toward all moments being equally real, and that the felt specialness of the present is a feature of being a physical process embedded in the block, not a feature of the block itself. The present feels special because you are a self-referential process, and the only moment you can directly access is the one your physical processes currently occupy. This is not a dismissal of the present. It is an elevation of it. The present is not special because the physics says it is. It is special because you are here, now, in it. That specialness is yours. It belongs to your experience, to your consciousness, to the extraordinary accident of being a physical system complex enough to have a point of view. The block does not have a point of view. You do. And your point of view, located at these specific coordinates in the four-dimensional structure of reality, is the only point of view you will ever have. Not because others do not exist, they do, at their coordinates, with their own felt present, but because yours is the one you inhabit. The present moment is not an illusion. It is the most immediate fact in your experience, but it is not a cosmic fact. It is a personal one, and there is something important in that distinction. Addendum 2: black holes, time, and the ultimate horizon. We have talked about time dilation, the slowing of time near massive objects and in fast-moving reference frames. But we have not talked about the most extreme case. What happens to time at the edge of a black hole? A black hole is a region of space-time where the curvature is so extreme that nothing, not even light, can escape. The boundary of this region is called the event horizon. And at the event horizon, something extraordinary happens to time. For an observer falling toward a black hole, time proceeds normally. They feel nothing special as they cross the event horizon, at least for a large enough black hole, where tidal forces are manageable at the horizon itself. They pass through the horizon and continue toward the singularity. But from the perspective of a distant observer watching the falling person, the picture is different. As the falling observer approaches the event horizon, the light they emit takes longer and longer to escape the black hole's gravity and reach the distant observer. The falling observer appears to slow down. The light becomes redder and dimmer as it is gravitationally redshifted. And at the event horizon itself, the falling observer appears from the outside to freeze. They never appear to cross. They are seen to approach the horizon asymptotically, becoming infinitely redshifted and infinitely slowed, never quite arriving. From the outside, the falling observer is frozen at the event horizon, preserved in a kind of eternal photograph, a perfect example, if you like, of the block universe at its most extreme. The frozen image at the horizon is there, in the block, at those coordinates, permanently. Time has not stopped for the falling observer. Their proper time continues, and they cross the horizon and reach the singularity in a finite proper time. But the moment of crossing, for the outside universe, is pushed to an infinitely late coordinate on the external time axis. Inside the black hole, the situation is even stranger. The singularity at the center of a black hole is not a point in space, it is a moment in time, the future. The singularity is the future, in the most literal sense. For anything inside the event horizon, the singularity is where all future time-like paths lead. You cannot avoid it any more than you can avoid tomorrow. This means that inside a black hole, the geometry of space-time has been so distorted that what was the spatial direction toward the center has become a temporal direction toward the future. You cannot escape the singularity for the same reason you cannot escape next Tuesday. It is simply ahead of you. Black holes are perhaps the most dramatic illustration of the fact that space and time are not fixed, independent things. They are aspects of a single geometric structure that can be warped and twisted to extraordinary degrees. And the block universe, the idea that all space-time coordinates are equally real, is not just an abstract philosophical position. It is the natural way to describe a universe that contains structures as extreme as black holes. The information paradox, the question of whether information that falls into a black hole is preserved or destroyed, is one of the most active areas in theoretical physics today. Stephen Hawking showed in 1974 that black holes radiate, they slowly evaporate through quantum processes, emitting what is now called Hawking radiation. The question is whether this radiation carries the information about what fell in, or whether the information is genuinely destroyed. Most physicists now believe, and there are increasingly strong arguments, that information is not destroyed. That even in the most extreme processes in the universe, the past is preserved, information is conserved, the block is not edited, the universe forgets nothing, not even what falls into a black hole. Addendum: 3 memory, records, and why we experience the past as gone. We have established that the past is physically real, that it exists at its space-time coordinates, that the universe preserves information. So why does it feel so completely gone? The answer involves memory, entropy, and a subtlety about how we access the past that is worth examining carefully. Memory is a physical process. When you remember something, you are not accessing the original event. You are accessing a reconstruction, a neural pattern that was formed at the time of the original experience and has been stored imperfectly, incompletely, subject to revision in the physical structure of your brain. When you remember a moment, you are accessing information about that moment that was recorded in your nervous system. You are reading a record, not visiting the event itself. This is a crucial distinction. The past exists at its space-time coordinates, but you do not have direct access to those coordinates. You have access to traces physical records left in the present that carry information about what those coordinates contained. The physical record of the past exists in many forms. In your memory, in photographs and video, in written documents, in the thermal state of the environment, the echoes of events in the distribution of heat and entropy. In the position of stars, when you look at the night sky, you are seeing the past directly. Light that left those stars years or centuries or millennia ago. In the cosmic microwave background radiation from 380,000 years after the Big Bang, still traveling through the universe, carrying information about the state of the cosmos at that early moment. The past is not absent. It is continuously present in its traces. The reason it feels gone is that our access to it is mediated by these traces, and traces are always imperfect, always incomplete, always degraded by entropy. Memory fades, photographs yellow, documents crumble. The thermal echo of an event disperses into the environment until it is indistinguishable from noise. This is what entropy does to the past. It does not erase it, but it dilutes the records. It spreads the information about past events through so many degrees of freedom that reconstruction becomes increasingly difficult. The information is still there, in principle, in the physical state of every atom that has ever been influenced by the event. But the practical accessibility of that information decreases with time, and there is an asymmetry here that connects back to the arrow of time. We have records of the past, but not the future, because records are made by low-entropy processes that convert structured energy into thermal waste. A camera takes a structured pattern of light, an ordered configuration, and converts it into a structured pattern in the emulsion or sensor. The process increases entropy. The film gets warmer. Energy is dissipated, but leaves behind a record. This is the generic mechanism by which the past leaves traces in the present. The same mechanism would, in principle, leave traces of the future in the present, but only if the future were caused by the present in the backward direction, which does not happen in a universe with our arrow of time. Future events are not caused by present events running backward. They are caused by present events running forward. The causal structure determines which direction leaves records. We are always in the middle of the block, looking back. The past is well lit by its records. The future is dark, because the records have not been made yet. This is not because the future does not exist. It is because the process of record-making runs in one direction, from low entropy to high, from past to future. The felt absence of the past is an artifact of how we access information about it. The past is there. We just cannot read it anymore, except through the traces it has left behind. Addendum 4. Why does time move forward? The ultimate question. We have answered the question of why you cannot go back to the past. We have argued that the past is real. We have described the thermodynamic, geometric, quantum, informational, and empirical barriers to backward time travel. We have talked about the block universe and the arrow of time and the strange comfort of a universe that forgets nothing. But there is one question we have not fully answered, and it is the deepest one. Why does time move forward at all? Why, given that the laws of physics are nearly symmetric and the block universe says all moments are equally real, do we have such a powerful and universal experience of time flowing in one direction? The short answer, as we discussed in the section on entropy, is because the universe started in a very low entropy state and has been moving toward higher entropy ever since. The direction of increasing entropy is what we call forward in time. But this answer immediately raises a deeper question. Why did the universe start in a low entropy state? This is one of the hardest questions in cosmology and physics. Several answers have been proposed. The most straightforward answer is, it just did. The initial conditions were what they were. There is no deeper explanation. The universe had a beginning, and that beginning was characterized by extreme order, and everything since has been the relaxation of that order. This is the past hypothesis, taken as a brute fact. A more ambitious answer involves cosmological selection. Some physicists, including Roger Penrose, have proposed that the low entropy of the universe's beginning is connected to the nature of quantum gravity and the collapse of quantum states. Penrose's conformal cyclic cosmology proposes that the universe goes through cycles, with the end of one cycle, the diffuse, cold, maximum entropy state of a heat-death universe being geometrically equivalent to the beginning of the next cycle. In this picture, the low entropy of the Big Bang is not arbitrary, but arises from the dynamics of the cosmic cycle. Other cosmologists, inspired by inflationary cosmology, suggest that the low entropy of our observable universe is a consequence of the dynamics of inflation, the period of exponential expansion in the very early universe, combined with the way quantum fluctuations during inflation were amplified into the structure of matter. In this picture, the apparent low entropy of our initial conditions is partly a consequence of the fact that we live in a relatively small region of a much larger universe, and the initial conditions in our region happen to be ordered in just the way required for inflation to proceed. Still others appeal to the anthropic principle. We exist because we are in a region of the universe with initial conditions that permitted the formation of stars, planets, and life. A universe that began in a high-entropy state would not produce observers to ask why it began in a high-entropy state. This is not a satisfying physical answer. It does not tell us why the universe has the structure it does, but it reminds us that the question of initial conditions cannot be separated from the question of who is asking. The honest answer, from the frontier of physics, is we do not fully know why the universe began in a low-entropy state. It is one of the deepest open questions. The arrow of time, the direction in which time moves for us, is explained by the low entropy of the beginning, but the low entropy of the beginning is not yet fully explained. What we can say is that the arrow of time is real. The universe moves in one direction. The past is where it came from. The future is where it is going. And the block universe, the permanent, four-dimensional structure in which all moments exist, has a grain that runs in one direction, from low entropy to high, from the Big Bang to whatever the ultimate fate of the universe turns out to be. You are a process that runs with that grain. Your memories run in that direction. Your causation runs in that direction. Your experience of time as a forward-flowing river is a reflection of the grain of the universe, read from the inside. And the past, that permanent, real, unreachable past, is behind you in the grain, not absent, not destroyed. Simply in the direction from which things came, in a universe that moves only away from its own beginning. One direction, one grain, and somehow, in the experience of beings like us, that grain becomes a river, and the river becomes the feeling of being alive. Thank you for watching. If this changed the way you think about time, even a little, drop a comment below. We read them. And if you have not subscribed yet, now is the time. There is much more of this kind of thing coming, and you will want to be here for it. End of script. Total estimated length, approximately 24,000 plus words. Addendum 5 time. Identity and the self that cannot return. There is a version of this question that nobody asks in physics papers, but that almost everyone feels at some point in their lives. It is not about the mechanics of time travel. It is about something more personal and more unsettling. Even if you could go back, even if you could step through a traversable wormhole and arrive at the coordinates of some earlier moment in your life, would you actually be returning to the past? Or would you just be visiting something that looked like it? This is not a riddle. It is a genuine, physical, and philosophical question about what it means to be the same person across time, and about what exactly is preserved when we say that a moment still exists in the block universe. Think about it carefully. You are made of atoms. Those atoms are constantly being replaced. The atoms in your body today are largely not the same atoms that were in your body 7 years ago. The cells have been replaced, the molecules turned over, the water cycled in and out. You are, in a meaningful physical sense, a different arrangement of matter than the person who lived your earlier memories. What makes you the same person is not the atoms. It is the pattern, the information encoded in the structure, the continuous thread of memory and causation that runs from your past self to your present self. You are the same person, not because you contain the same matter, but because you are causally continuous with your earlier self, connected by an unbroken chain of physical processes. Now, if you traveled back to an earlier moment in your life, you would find a version of yourself at that time, the self who actually lived that moment. That self is at those coordinates in the block. But the self doing the traveling is also there, arrived from the future. There would be two of you, and the one who arrives from the future is not the self of that moment. It is a later self, carrying memories and patterns that the earlier self does not yet have. The moment you are trying to return to is, in the most personal sense, not recoverable. It was that version of you, in that configuration, experiencing the world with that particular set of memories and knowledge and physical state. Even if you could visit the coordinates, you would be a visitor. The experience of being the person you were then that is gone in a way that has nothing to do with space-time geometry. This is a different kind of loss than the geometric inaccessibility we have been discussing. It is a loss that would persist even in a universe with traversable wormholes. The past exists at its coordinates. You have changed. You cannot be the person you were then simply by going there, any more than you could become a child again by returning to your childhood home. The philosopher Derek Parfit spent much of his career on this question, on what personal identity over time actually consists of, and what it means to say that you are the same person as the child who shares your memories. His conclusion, broadly, was that personal identity matters less than we think, and that what matters is psychological continuity, the overlapping threads of memory, intention, and character that connect different temporal stages of a person. In Parfit's view, the question, could I return to the past, partly dissolves when you realize that I is already a kind of fiction, a convenient label for a process that is continuously changing, continuously becoming something slightly different, never quite the same from one moment to the next. The self you were at any given past moment was a real physical process. It was located at those coordinates. In the block universe, it is still there, but it is not quite you. It is your predecessor, your ancestor, the version of the process that led to you. And this is, in a strange way, a kind of comfort. You are not just one static thing in the block. You are a world line, a continuous thread of causally connected moments, each slightly different from the last, stretching from birth to death. Every point on that world line is real. Every configuration of the process that is you is permanent in the block. You did not lose your past self when you moved on from them. They are still there. They are just not where you are anymore. And every future version of you, every moment of your life that has not happened yet, is, if the block universe is fully correct, equally real, already located at its coordinates, already permanent. You are, in the block universe, a line drawn through 4 dimensions, and lines, once drawn, do not disappear. Addendum 6, the physics we don't yet have, quantum gravity and the nature of time. We should be honest about the limits of what we know, because there is a deep sense in which everything we have said in this video, everything about the block universe, about the arrow of time, about the permanence of the past, is built on physics that is not yet complete. Special relativity is complete. General relativity is complete, in the sense of being a fully formulated theory with extraordinarily precise predictive power. The second law of thermodynamics is solid. The standard model of particle physics, including CP violation, is well tested. But these theories have not been reconciled with each other in the regime where reconciliation matters most. The Planck scale, the scale at which the quantum properties of matter become relevant to the geometry of spacetime itself. General relativity treats spacetime as a smooth, continuous geometric structure. Quantum mechanics describes physical quantities as discrete and probabilistic. These descriptions are incompatible at the Planck scale, roughly 10 to the power of negative 35 meters, and at the energies corresponding to that scale. And it is at those scales that the most fundamental questions about time live. The 3 leading candidate approaches to quantum gravity: string theory, loop quantum gravity, and causal dynamical triangulations, all have different things to say about the nature of time at the deepest level. In loop quantum gravity, as we discussed earlier in this video, space and time are discrete at the Planck scale. They are built from fundamental units, like pixels, but in 4 dimensions. Time is not a smooth background, but a series of discrete steps, each one a quantum transition from one configuration of space to the next. In this picture, the block universe is not quite a smooth 4-dimensional continuum. It is more like a granular network, with a minimum possible temporal interval. In string theory, the fundamental objects are not point particles, but one-dimensional strings vibrating in a 10 or 11-dimensional spacetime. Time, in string theory, behaves differently than space. It is special, in a technical sense, related to the properties of the string world sheet. The details are too technical to go into here, but the picture of time that emerges from string theory is not obviously a simple block universe. It is something richer and stranger. In causal dynamical triangulations, developed by Renate Lowell, Jan Ambjorn, and Jerzy Jurkevich, Space-time is constructed by gluing together tiny simplices, four-dimensional generalizations of triangles, with the constraint that the causal structure, the distinction between past and future, is preserved at every step. This approach explicitly builds the arrow of time into the construction, rather than trying to derive it from statistical mechanics. The results, in computer simulations, produce a space-time that looks smooth and four-dimensional at large, scales a good sign, and shows quantum fluctuations at small scales that are consistent with what quantum gravity should look like. All three of these approaches are incomplete. None has made a confirmed experimental prediction that distinguishes it from the others, or from general relativity in the regime we can currently test. The energy scales involved are roughly 16 orders of magnitude beyond what the Large Hadron Collider can probe. A particle accelerator that could directly test quantum gravity would need to be the size of a galaxy. This does not mean we are helpless. There are indirect tests, implications of quantum gravity, that show up at accessible scales through subtle effects. The polarization of light from gamma-ray bursts at cosmological distances, correlations in the cosmic microwave background, the spectrum of Hawking radiation, if we ever observe it. These tests are being pursued, and they will constrain the possibilities. But for now, the honest position is, we do not have a complete theory of quantum gravity, and without one, we cannot fully answer the question of what time is at the most fundamental level. What we can say is this: every approach to quantum gravity takes the block universe idea seriously, at least as a starting point, and some approaches push it even further, suggesting that time is not fundamental at all, but emerges from something timeless. If the Wheeler-DeWitt equation is right, the universe's wave function has no time argument. Time would then be an emergent, approximate description of a timeless quantum structure, the way temperature is an approximate description of the average kinetic energy of many particles, rather than a fundamental property of any individual particle. If time is emergent, then the question of why we cannot return to the past becomes simultaneously harder and more interesting. It is not that the past is blocked by the geometry of space-time. It is that the very concepts of past, present, and future are approximations, useful at the human scale, but not fundamental at the Planck scale. The past we cannot return to is not a fixed location in a more fundamental structure. It is a feature of the emergent description we use to navigate an underlying reality that may be quite different from anything we have yet imagined. We are at a frontier. The tools are being built. The questions are being sharpened. And the fact that we can even ask these questions, that physics has taken us from Newton's absolute time to Einstein's relative space-time, to Hawking's evaporating black holes, to the Wheeler-DeWitt equations, vanishing time in the space of roughly 3 centuries, is itself extraordinary. The physics of time is not finished, but what it has found so far is already enough to permanently change the way you see the universe and the way you see yourself in it. The past exists. You cannot reach it. Every moment you have ever lived is permanent. You are a line through time, not a point. And the universe, at every scale we have probed, is structured in a way that keeps its own history, even when it forgets how to tell it. Final reflection: what this means right now. You have been here for a long time. This video has asked a lot of you. It has asked you to sit with ideas that are genuinely counterintuitive, to follow chains of reasoning into places that most people never go, to take seriously what physics has actually found, rather than what it would be comfortable to find. So let us end simply. Every moment you have ever loved is real. It is located somewhere in the structure of this universe, at coordinates that physics can describe, even if we cannot visit them. The universe did not consume those moments and throw them away. It kept them. It keeps everything. You are moving forward, carried by entropy, by the arrow of time, by the extraordinary improbability of the low-entropy universe you were born into, and you cannot turn around. Not because there is nothing behind you, but because the grain of reality runs one way, and you are part of it. The past exists in its permanence. The future exists in its uncertainty. And you are here, at the needle's point of the present moment, which is the only place in the block where anything is actually being experienced. That is not a small thing. That is everything. Go look at something beautiful. Call someone you have been meaning to call. Take 5 extra seconds with something ordinary. Because the moment you are in right now is in the process of becoming permanent, of joining the block, of taking its place among all the moments that have ever been, and it deserves to be worth keeping. Physics does not often give you that kind of instruction, but it has earned it. If you made it to the end, genuinely thank you. This took a long time to research and write, and it exists because people like you actually want to understand things deeply, rather than just have them described from the surface. Leave a comment. Tell us what part hit hardest, or what question this left you with that we did not answer. We read everyone. Subscribe if you have not. There is more where this came from, and none of it is surface level. Like if it helped, share it with someone who would appreciate it. We will see you in the next one.